Good afternoon. My name is Kacyn Ideue, and thank you so much for joining me for my talk on how environmental factors affect oyster growth in Hawaii. I'm sure many of you may be wondering how I got into oysters in the first place. Well, I've always been someone who strived to help the environment, so I knew that I wanted to find a project that helped the environment in some way. My teacher suggested a project involving oysters, and the moment that I found out that these small creatures people normally saw on their plate could in fact help the environment, I was hooked. People often overlook oysters and only perceive them as a yummy dinner. However, they are so much more than that and can actually serve a purpose that is helpful to the environment. I'm sure that many of you already know or realized that the Ideue Canal and many of Hawaii's waters are severely polluted. However, did you know that oysters can help this problem? Oysters are able to actually clean water and improve the overall water quality, as these bivalves are considered filter feeders, meaning that they can filter water through their daily life habits, such as eating. By filtering water, oysters are able to clean large bodies of water in record times and are known to improve the overall water quality as well. In order to filter and clean water, oysters use their specialized organelles to aid this process. The most notable organelle for water filtration is known as the lateral frontal cirri, located in an oyster's gills. In order to be the best filter for harmful contaminants, the lateral frontal cirri needs to grow to its maximum. However, environmental factors such as water temperature, salinity, and turbidity can affect the growth of this organelle. Thus, oysters need to stay in the correct range of these environmental factors. So, as I mentioned before, environmental factors are known to play a crucial role for oysters and their lateral frontal cirri growth. Additionally, the environment is also known to play a critical role in the overall growth and mortality rate of oysters. From previous research, it has been noted that oysters will experience an increase in their growth rate in water temperatures from 25 to 26.1 degrees Celsius, while a salinity level of 22 to 30 ppt will also show the most oyster growth. In terms of turbidity levels, oysters will show a decreased growth rate and an increased mortality rate if they are exposed to turbid environments or if they are in a turbid environment suddenly for a large amount of time. Additionally, river flow has been known to promote E. coli, Haplosporidium nelsoni, aka MSX, and the bacteria Parkinsonis marinus, aka Dermo, development. The results of exposure to these bacteria will result in a decreased growth rate and the further development of oysters. Additionally, it has been noted that freshwater floods are harmful to oyster development. As freshwater floods flow into the Ideue Canal or other salty bodies of water, it results in a decrease in salinity and the overall water temperature, which is harmful for oyster growth. All of the information that I've shared from the last slides only apply to oyster species outside of Hawaii's native ones, and the environment the research oysters were in were not from Hawaii. Therefore, does this research apply to oysters in Hawaii? The answer to this question is no. Hawaii is actually the gap in research. Currently, there is little information on how Hawaii's native oysters are affected by our native environment. Thus, the gap in research led to my research question, which is, how do environmental factors affect oyster growth in Hawaii? From the previous background knowledge I've gained, I made 3 hypotheses in order to answer my research question. My first hypothesis concerns the environmental factor of water temperature, which states that oysters will have an increased growth rate and a decreased mortality rate in water temperatures 25 to 26.1 degrees Celsius or higher. However, a decreased mortality rate can be seen in temperatures up to 28 degrees Celsius, as oysters have experienced this type of environment in Hawaii. The next hypothesis concerns salinity and states that salinity levels between 22 to 30 ppt will produce the most oyster growth and the least mortality rate. The last hypothesis regarding stream discharge level states that oysters will grow the most and will have a decreased mortality rate in river flows that are less than the median. From the results of my work, my conclusion will have a positive impact on the community. First, it allows researchers to learn where the best place is to put oysters for maximum improvements on water quality. Second, my results will allow for scientists to learn which environmental factors are the most harmful and important for oyster growth. Thirdly, my conclusions will aid in waterline restoration projects to help those working on such projects identify key factors in the environment that can affect the habitat quality of nearshore areas. So in order to research a conclusion, I first received oyster growth data and mortality rate data from my mentor, Dr. Ann Brazier. The oyster growth data and mortality data are part of a project from the Oahu Waterkeepers led by Dr. Brazier. This project aimed to use native oysters to promote the mission of the Oahu Waterkeepers to provide, quote, fishable, swimmable, and drinkable waters on Oahu, unquote. In order to measure the growth, oysters were given a number from 1 to 100, 1 to 50 for AWWC, and 51 to 100 for AWHC, and were measured by length for the growth in millimeters. The oysters were measured on the dates 9/17/2019, 10/15/2019, 11/15/2019, 12/3/2019, 1/28/2020, and 3/24/2020. Then I found publicly available environmental factor data sets on water temperature, salinity, and stream discharge level. However, it should be noted that the two gauges to measure environmental factor data weren't directly next to the two oyster locations. Salinity and water temperature data sets were gathered from PAC-IOS, while the stream discharge level data sets were gathered from the USGS sensors. Although there were Alawai Canal sensors for water temperature and salinity, there were no stream discharge level sensors for the Alawai Canal. Thus, upstream sites were used in lieu of the Alawai Canal to measure stream discharge level. These locations were Waiakea Stream, Pukele Stream, Manoa Stream, and Manoa Pololo Drainage Canal. I then made spreadsheets of water temperature and salinity levels in order to organize the data in both Excel and Google Sheets. In addition to spreadsheets, two tables were created with the mean water temperature, mean salinity, oyster growth rate, and oyster mortality rate to help with data organization. Both tables had the same mean temperature, mean salinity, and mortality rate data. However, one table had the oyster growth data for the AWWC location, and the other had the data for the AWHC location. After making the tables, box plots were constructed using the oyster growth data. Box plots were made per oyster, and the data showed that the oyster growth changed over time. After creating these tables, graphs of the total time period during the collection of oyster growth data were then made using the spreadsheets of the water temperature and salinity data and Excel, while the same type of graph was created using the R program for the stream discharge level locations. After making the graphs, they were boxed according to the time period in which oyster growth was collected at. After boxing the graphs, a horizontal line was drawn on all of the stream discharge level graphs at their respective medians in order to indicate potential peaks. Peaks were defined as anything that exceeded the median line on the graph and were used to create conclusions for the stream discharge level factor. From this graph of the discharge of Manoa Pololo Drainage Canal and the salinity over time, we can see that a correlation between the floods and salinity levels occur. This means that as more water floods come, the salinity levels in the Alawai Canal will rise. This relationship holds true as the water floods occur during the winter time, where Hawaii usually sees more floods occurring. From this graph of temperature over time, we can see that the overall water temperature decreases as time goes on, and the decrease in water temperatures correlates to the winter months. This relationship is important as it depicts the events of freshwater floods as the overall water temperatures have decreased over time. Going back to the previous background research, it was noted that a decrease in water temperatures due to flooding will have a negative effect on oyster growth, which has been noted in the data. After these observations were made, the two tables were then used to create simple linear regressions in the R program. There were 8 different graphs that were created from the simple linear regression model between the AWWC site, AWHC site, mean water temperature, mean salinity, oyster growth rate, and oyster mortality rate data. However, only the temperature versus mortality and salinity versus mortality regressions were statistically significant. After the graphs were created, the R squared, adjusted R squared, and p-value were determined for each graph. If we take a closer look at the temperature versus mortality regression, the overall takeaway is that as the water temperature increases, mortality rate will decrease. This relationship between temperature and mortality further bolsters the relationship seen in the temperature graph, as it depicts that a lower temperature will in fact increase mortality rate, which coincides with the previous background information. In the salinity versus mortality graph, the takeaway here is that as salinity increases, the overall mortality rate for oysters will decrease. This relationship between salinity and mortality further supports the background information about flood events, which states that lowered salinity levels from flood events are harmful for oyster growth, which is exactly what happened here as the mortality increased when oysters saw a lowered salinity level. After making all of my statistical figures, I managed to reach an overall conclusion from my data. The conclusion that I made was that as water temperature decreases, the mortality rate of oysters will also decrease, while an increase in salinity will promote a higher mortality rate. I couldn't reach a sure statistically significant conclusion for the other variables in my project, as all of their graphs could not reject the null hypothesis. A rejection of the null hypothesis states that a relationship between x and y variables are only true if they have a p-value that is less than 0.05. In addition to the overall conclusion to my project, there is also a major takeaway from the data analyses. Since there were only 5 time periods, it's important to consider that this could be a reason why the null hypothesis couldn't be rejected for the rest of the other graphs. Going back to the previous background research, my conclusion does not refute nor agree with the studies done on turbidity. Since the turbidity sensor from the Ideue was out of commission during the time frame of the study, no new data could be gathered and analyzed. In terms of water temperature, previous research indicated that the oyster growth rate would increase when bivalves were exposed to temperatures of 25 to 26.1 degrees Celsius. However, the results of the study refuted the previous research, as oysters experienced a higher mortality rate instead. In regards to salinity, the conclusion to this experiment proved to further support the previous research, as oysters experienced a higher mortality rate when exposed to a higher salinity level. Since bacteria level was not studied at this point of the experiment, a conclusion on whether this study further refutes or bolsters previous research cannot be reached. Finally, other researchers can apply from and learn from the conclusion from this project. Since temperature and salinity are important factors in oyster mortality, other researchers can look to moving the oysters when these environmental conditions increase. Perhaps moving the oysters deeper in the Ideue or in the shade could be some management options or actions to promote a decrease in the mortality of oysters. Based on the conclusions of this project, future research should encompass looking at more time periods to see if the other relationships between oyster growth, water temperature, and salinity becomes statistically significant. Additionally, investigation into the relationships of the other environmental factors mentioned in the background should be conducted to provide an overall conclusion. If this further research can be conducted, then an overall conclusion on how environmental factors affect oyster growth in Hawaii can be established. Next, some advice for some future researchers. First, my advice would be to pick a project that you are generally interested in and can see yourself doing for a whole school year. Additionally, I would also say to take this course to try new things in the science world that you've always wanted to explore. There are so many tools and resources that are available to you in independent research. Last, I would like to say to have complete confidence in yourself and your capabilities as a scientist and as a researcher, because you can do anything. So finally, some acknowledgements and advice. I would first like to thank Dr. Chen, who has been so supportive throughout this research process, and who is someone I can repeatedly turn to for advice and assistance. Secondly, I would also like to thank my mentor, Dr. Brazier, for providing her expertise and constant help and support throughout my research. Third, I would like to thank my research class for being the best peer editors and a constant wave of support and encouragement as we've all been through this process. I would also like to thank my parents and friends for always giving me words of encouragement and support whenever I needed it. So here is my picture bibliography, and we're excited. Thank you.